Hi, everyone. Okay, so this is the recording of the review session. I'm just going over everything we went over today already. And yeah, this will be the only one I'm re-recording this semester. The other ones I'll be sending you guys are going to be from the review sessions from last semester, but we'll cover over the exact same things. We will get started. So the first part is going to be kind of a review. And then in another video, I will send out the explanations for the quiz. This will be kind of brief. We'll just go over the basic topics and the basics for those. Okay, so hybridization, the main things you need to know is to kind of be able to recognize when something is SP, SP2, SP3, and then what a diagram might look like for those respective atoms. So let's say we have a molecule, something that looks like this. All right, so if we're looking at this oxygen right over here, we know it has two lone pairs there, even though we don't initially write them in. So it has two lone pairs, and it has this bond with hydrogen and this bond with the carbon right over here. So in total, it's kind of, there are four electron groups, kind of things that bear electrons around it. So four kind of those entities. So 1, 2, 3, and the carbon would be the fourth one. Those are four things surrounding this oxygen, and that's how I'm going to consider sp3 with those four entities or four things around them. Okay, so this oxygen right here would be sp3. Okay, and just so we're clear, it has 6 valence electrons. That'll be important for the diagrams. So oxygen has 6 valence electrons, nitrogen has 5, carbon has 4. Okay. So if we were to look at this oxygen over here, it's a little bit different. It has a double bond. It still has those two lone pairs there. And so if we count how many things it's connected to, 1, 2, those lone pairs are each, one thing. And then the carbon over here would be 3. So this instead would be sp2. Okay, so sp2, there are 3 things surrounding it. And again, oxygen has 6 valence electrons. Okay, and then over here we have some carbons. So this might be a little bit confusing. What's going on here is there's actually 4 carbons. There's a carbon here, a carbon right there, and right here. Okay, and so if we were to ask ourselves what hybridization the carbon right here was, well, it would be connected to the carbon here and the other carbon here. So those are 2 things. Okay, so 1, 2. That would be sp. All right, so if we ask ourselves, what would this look like on a hybridized diagram? So for our first example right over here, which is going to be sp3, they all have either sigma bonds or lone pairs. They have no pi bonds. Pi bonds are in like double bonds or triple bonds, but sp3 is usually just none of those. It only usually has single bonds, and all of these will be labeled like sp3, all of them, and they're going to be on the same plane. Okay, so this will be energy right here, and like I said before, oxygen has 6 valence electrons, so I'm going to label it this way. Okay. The other one we're looking at again was oxygen over here, but this was sp2 instead. So I'm adding a p orbital here because there's a pi bond. So in a double bond, there's a sigma bond and a pi bond. That pi bond is going to be, or the p orbital is going to be raised. It has more energy. Okay. The rest of these are going to be sp2. And again, oxygen has 6 valence electrons. This is oxygen, sp3. This is sp2. Okay. So then the last example we were talking about is sp over here. So this is a carbon sp. So carbon has 4 valence electrons. This time we're dealing with a triple bond. So triple bond has 1 sigma bond and 2 pi bonds, so 2 p orbitals. Okay, hopefully that makes sense. All right, so those are the basics of what you would need to know for hybridization. Now we'll move on a little bit to nomenclature. So for naming, the first basic rule would be to find the longest chain. With the most substituents. Okay. So if we did that over here, we just looked for the longest chain with the most substituents. That would be over here. And then we have to ask ourselves, which direction are we going in? Are we labeling this, this way, left to right, or are we labeling it right to left? So in that case, we need to ask ourselves to find which side we are going to start from. Start from side in which you hit the first substituent first. Or because sometimes you'll have a molecule, it'll look something like this, where you run into the first substituent if you're going this way on the second carbon, and if you're going this way also on the second carbon. So in that case, you need to look for where you'll find the lowest numbering scheme. So that just means the lowest numbers in your name, basically. So like 2,4 diethyl something will be a lower numbering scheme than 3,6, for example. Okay. If we were to look at where our lowest numbering scheme is here, then it would have to be this way. Okay, so let's see why. I'm going to label what numbers our substituents are. So 2, 3, I believe this is 6. Okay, so we have 2, 3, and 6. That's our number scheme. And then if we were to go the other way, maybe 3, 6, and 7, which is a lot, which are bigger numbers. Okay, so we decided this is 1, 2, 3, 4, 5, 6, 7, 8. All right, so our base name is octane. We have a substituent here, here, and here. Okay, so I'm just going to write out what those are. So that's kind of the third step, is figuring out what your substituents are. So we have 2 methyl, 3 ethyl, and 6 chloro. You want to make sure you put this in alphabetical order. Not everything counts for alphabetizing. For example, the di, tri, tetra in alphabetizing doesn't count. So if you had dimethyl, the N would count. And then also, if you have sec-butyl or tert-butyl, the T in tert wouldn't count, the B in but would. Or in sec-butyl, it would be the S in sec, and the S in sec would not count, and then the B would. In isopropyl, though, for example, the I still counts. It's just isopropyl, one word. Okay, so when we put this all together, And that's our final name. Okay. So now we're going to take a little bit of a look at functional groups, because I know they can be confusing. Unfortunately, you have to commit them to memory. I recommend just writing them out as many times as you can, as many times as it takes for you to remember them without a reference. So this molecule is actually just a polypeptide. And yeah, so it actually spells out the sequence. So amino acids have a code, an abbreviation code, and this spells out per aspera ad astra, which means through difficulty to the stars. I actually am planning, hopefully, on getting this tattooed one day. And yeah, because it really connects, you know, amino acids, biochemistry with our pursuits to space. So anyway, so let's look at the functional groups here. We have an amine here. What kind of amine? This is actually secondary amine. I'll explain secondary, tertiary, primary, what that means. So we have secondary. We actually have an amide here. Okay, when we look at an oxygen in proximity to a nitrogen connected just by one carbon here, that is an amide. Here is a carboxylic acid. Let's see, this is part of another amide. If this was just by itself, it would be a ketone. But we want to think about the more complex structure, the more complex functional group. So we would just consider the bigger one, the amide. What else? We have some more amines here. And let's see. So I'm going to show you the difference between each of these amines. So I can't highlight here. So each of these amines, so a primary amine would be something like this, okay, where it's a nitrogen connected to two hydrogens and then one R group, the R group meaning anything, okay. And then a secondary amine, like over here, oh, sorry, that's tertiary. A secondary amine, like over here, would be a nitrogen connected to one hydrogen, but then two of those R groups, okay. And then this would be a tertiary where there's three R groups coming off, okay, of that nitrogen. What else? So we see an alcohol right there. And I think that's pretty much it. I don't think there's anything else. Okay. Then over here, I just want to emphasize what an ester looks like, because it could be confusing sometimes. So this is actually an ester. So an ester is just it has this signature kind of ketone with an oxygen right next to it, and then an R group coming off of that oxygen. That contrasts to a carboxylic acid, which just cuts off right here with the hydrogen. Okay. All right, so we have that ester, and then we also have an alcohol and a benzene right over here. Okay. So I also want to talk a little bit about acid base, the difference between a strong acid base and a weak acid base, what they mean. So strong acids and bases have a Ka or Kb, just equilibrium constant greater than 1. Okay, what does this mean? This means that the right side is favored, the forward reaction that's favored, like if we did HCl plus H2O, the forward reaction going right would be completely favored. This was completely dissociate, okay? Whereas if we had a weak acid base, the Ka or Kb, just the K, this is the dissociation or equilibrium constant would be less than 1, which means that if we had like something like HCN plus water, we try to do this, reaction, then actually the left side would be favored. Okay, we're not going to get so much of the right side happening. So yeah, not much of the actual acid reacts with the water. And in fact, the left side, the backward reaction, the reverse reaction is favored. So that's what that means. The Ka, Kb values, these are intrinsic properties of the acid, intrinsic properties of how they disassociate with water. Okay. So some strong acids, you do again need to commit these to memory. They're really important. One tricky thing is that these all have like the halogen. They're like HCl, HBr, HI. The only one that's missing is HF, and that's actually HF is a weak acid. Okay, so don't get that confused. Again, please reference your equation sheet for all of this stuff. But you'll have to memorize all the weak acids and bases are on the equation sheet, but all the strong ones you need to memorize. Okay. Another tricky one is HNO2 is a weak one. Okay, but HNO3 is a strong one. What else? HClO is a weak one, but HClO4 is a strong one. Okay. Then for strong bases, all of them with OH minus groups are going to be strong ones. Okay. So I also wanted to write out a little bit how you should tackle weak acids and bases. And just by the way, another thing you should know is acids and their conjugate bases have kind of an opposite relationship, the inverse relationship. If you have a relatively strong acid, its conjugate base is going to be relatively weak, okay? And the reverse is also true. Okay, so how you should tackle weak acid-base problems compared to strong acid-base problems. Like I said, strong acids and bases completely dissociate and react with water so that the concentration of the acid, so the concentration of HCl is equal to the concentration of H+, which is the reactant, which is the same as H3O+. So if I were to finish my equation right here, right, reaction. Okay, so my initial here, let's say I had 1.2 molar as an ice table. We don't really do ice tables for strong acids and bases because they're kind of pointless. Because all of this turns into, all of the reactants turn into products, okay? So there's no point in doing the ice table because this is always what we're gonna see, okay? And so that is why when we do negative log to find the pH, we can use, like, let's say this was our initial concentration, we can do negative log of 1.2 molar to find the pH for an acid because the initial concentration of HCl is equal to the H3O+ concentration, okay? Okay. For weak acids and bases, this is not the case though. So because such a small amount of it actually disassociates, we have to find it using the Ka value and blah, 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 and then we can find the pH, okay? So let's say we have 1.2 molar of HCN, and then we're doing our ice table. So we have our initial change, equilibrium. So we're gonna do minus X here, plus X here, plus X. And you don't need to worry about this minus over here because if you do 1.2 minus X, I'm telling you right now, the X is gonna be extremely small. And so it won't change your answer at the end. So I'm just gonna round that to 1.2. We're gonna have X here. We don't know what X is yet, but we can find it out. So using the Ka value for HCN, I think it's 6.2 E negative 10. So we can do that equals our products, okay, products over reactants. All right, we always want to take the equilibrium point. So we're gonna do X squared, so X times X divided by 1.2. Okay, then we're gonna solve for X. Let's say X I can actually calculate this really quickly. Okay, so this will be our value for X. And then what is X equal? Why do we just do this? So X, remember, is equal to the H3O plus concentration, which is the same thing as the H plus concentration. And why is that important? Because the formula for pH is negative log of the H plus concentration. Okay, so then we just need to do, to find the pH, we just need to do negative log of this. Okay, and if we did that, we would get pH of 4.56. Okay. All right, we'll do more examples of this. If we're dealing with bases, we only want to use KB. Okay. We only are looking at the OH concentration. We're only looking at POH, and then we can convert to pH after we're done messing with all that. But definitely keep acids and bases separate. It's really easy to mess up on the quiz with that. I can't even tell you how many times I've gotten problems wrong because I just overlook Ka or Kb, just switching them up, or I input the POH instead of the pH. It's a really easy mistake too. Okay. So now we're going to look at ranking of acids and bases. Usually, you're just going to have to rank between weak acids and bases, and you'll use the Ka, Kb. But if you're given the structures and have to figure out how to rank them due to the structures, the way to do that is by considering how to make the conjugate base more stable. Okay, so an acid becomes stronger when the conjugate base is stabilized. Okay, why does that matter? So for an acid to comfortably, willingly deprotonate, it has to be comfortable, has to be stable in its base form, right? In its conjugate base. It's going through this transition from an acid losing its proton and then becoming its conjugate base. It has to be okay to do that. It has to have a stable, let's say, future, a stable form of the conjugate base. So the way, so stronger, how to make an acid stronger? Acid strength by conjugate base stability. Okay, so how do we increase its conjugate base stability? Well, by making it comfortable and okay losing its proton. So there are two ways to do that. The first way is resonance. It's the most important one. So what is resonance? Resonance is basically electron sharing. So whenever you see something like this, okay, and whatever could be here, it doesn't matter. So I'm just labeling that R. When this becomes the conjugate base or whatever, it'll be something like that. Okay. But that resonance is right over here. Okay, so that resonance, we'll go ahead and share that electron, those electrons, with the other oxygen and make it more comfortable losing that proton. And then, yeah, so this is a more stable conjugate base. So resonance. Okay, and then the next one would be the inductive effect. Okay, and when the inductive effect, that just means having those electronegative groups. Okay, fluorine, bromine, chlorine, iodine will act as a support and again stabilize that conjugate base. So with those electronegative atoms, we want to remember the closer the better, so proximity. The other component would be what kind of atom it is. So the more electronegative, the more supportive. So fluorine is most electronegative, then chlorine, then bromine, then iodine. Okay. Last thing we want to consider is the amount. If we have more, that's more supportive. Okay. All right. So we'll look at an example of this in the practice quiz explanation. Okay. Last thing I want to cover is the autoionization of water. So water goes through an acid-base reaction by itself with itself. So okay, it'll look something like that. That's not a balanced reaction, but that's okay. We just got the basic idea here, what's going on. And so what's happening here is it's acting like an acid and base by itself. Why is this important? Okay, well, the reason it's important, the Ka and Kb of water is going to equal 1e negative 7. This gives the Kw value of 1e negative 14. Okay. If we have an acid or base come in, let's say HCN, and the concentration is 1e negative 10. Okay. That is too low for it to even change. So the pH of water at its neutral state with the ionization going on is 7. Okay. When you want to add some HCN, this concentration is way too low that the autoionization of water is more powerful and more triumph than any of the HCN, because it's such a small concentration. Anything lower than this, okay, anything lower than 1e negative 7 concentration will not have any effect on the pH. The pH will stay at 7. Okay. Okay, that's all I want to say about that. And then I will cover the quiz in the next video. Okay.